3 straight days. So I hope I do not burden you more with more some of the complicated stuff. But I'll just continue what I was talking yesterday. So we had a discussions on the basic ideas on topological matter, geometry, and topology in condensed matter system. And I introduced this the K-space, how this K-space is actually acting as a parameter that we can manipulate, actually we can rely on to review the topology on this K-space. So we ended up at this point that this is the usual growth function that with a periodic Hamiltonians with periodic potential. So we can identify this first moment of K, and we can back transform this kind of unitary transformation. We back transform to get rid of this extra phase. Then we're getting a fully periodic basis functions connected to the original growth function an eigenvalue. So once we have this one, then we have all these so-called Berry connections, which is corresponding to the vector potential in electrodynamics that we all know well. And then we can actually integrate this vector potential along some closed path, which is actually equivalent to the flux of that surface penetrating to this surface. That's we call curvature. That corresponds to the magnetic field in electrodynamics too. So all these things that we now know that this the periodic wave function that we define in the Hilbert space, it can be a playground for having this defining geometry on those space. So before we move further, let me just talk a little bit more about this binomial function. Yesterday, I defined this by integrating over all of this growth function of the K-space for certain eigenvalue n. Then actually, originally it was all periodic function with this oscillating function, but it can end up with some localized function within certain sites. Let's say it's a 0 site. Then we can also do a translation operator of the original growth function by R, means that we are starting from 0 site, then we move n times over somewhere with position R, then the same wave function will be translated to this green one to blue one. So every site has localized wave function, but that's just unitary translation of the same function to different sites. Well, this is just one-dimensional manifestation of this wave function, but it acts in 3 dimensions with space too. So once we have this space, then we can actually define this polarization, which was a very ill-defined quantity and space. But now we can actually work on a little different way. Let's say that we have the value function defined on site 0. Well, let's take this as a 0 site. Then we have a positive ion which is setting on periodic way, so it goes like that. And this binary function on this side will sit like this. I just make the pictorial way, which is actually better to understand than realistic wave function. Now the thing is, if I recap, the problem we had was if I take the unit cell like this, then we have a polarization like this direction. But if I take a unit cell like this way, then we actually had polarization to the other way. That was a ill-defined, what it means by ill-defined quantity. Now, the thing is, for this case, once we have this binary function, then we take the expectation value of this binary function, which is kind of well-defined quantity because W0, the binary function at site 0, is just localized only on this site. It actually has some tail, which is actually very important because to maintain the orthogonality between these two. But Well, just to take, but that's a kind of minor stuff, but quite important. But this wiggling of this binary function is just decaying. At least in one dimension, it is exponentially decaying. So it goes to like a very localized function. So we just try to take the expectation value of this the binary function with respect to position operator x. Oh yes.
There is a term called maximally localized.
Yes.
What is the difference between localized
versus maximally localized? Actually, that's another big story. In fact, this definition of this binary function is not unique, because at any k point, this wave function can have arbitrary extra phase, right? So depending on how you add up this extra phase, this W0 can be, extended far away, or it can be very localized, right? So you have to tune that additional phase of this integration to make this one as the minimally. Actually, the minimally space means maximally localized in that. So it depends on how you tune, add up some phases on top of this wave function with respect to k. That's global phase, so we can choose whatever we like. So that's an extra degree of freedom. Then you know how to optimize that, by calculating the dispersion of this spread of this wave function. So we put in some algorithm, and there is a nice way of Susan and Vanderbilt's work of that paper. They actually made very wonderful theory about it, and actually implemented it in Vanya 90 code, which now nobody cares about how it goes in detail, but you know how to make it. In fact, there could be some better way to do it, but anyway, this choosing this arbitrary phase is it's another big business that we have to think about, because in some case, the band touches. I mean, we can find this certain group of binary functions that we try to optimize, but if this bands overlap at some point, then it's hard to actually distinguish the one in one group to another one, right? So the touches means it's a metal, it's not an insulator, or they can overlap. So in such case, then we have some trouble. Physically, it's maybe not relevant, but that's another big subject that to go through. But yeah, but at the moment, at this talk, we just assume that we have an insulator and well-defined manifolds of band, so we don't have to worry about all these details. So anyway, so yeah, that's what it comes. So depending on this extra phase we put in, this one can go back to original band, actually glow states, extended far away. But anyway, so once we do this, then we can actually calculate this position of this. Oops, it's not it. Okay. Yeah. So once we define this position, then this one is exactly translated by this kind of very connection that we have defined. So we know the position of this the binary function. Then the polarization is well defined as far as we know how this one is attached to that. But anyway, so the way that you get through is that so the point that I like to make is this binary center. What we mean binary centers. So if you look at that, this binary function is this kind of localized wave function we define. So we are emptying position operator, which is actually same as if you put it inside. It's by taking this periodic basis that we have this extra phase HVIKR, and you take this derivative with respect to k, which is a parameter in our case. So we can take the gradients of k, then we take r, which is equivalent to this operator. So this r over here is an operator. Then that is actually what if it's integrate by parts, but there is a boundary condition usually. But if you just skip that, then we end up with that. And that, which is actually equivalent to having this position operation is actually calculating vary connection in k-space. It's hard to match and directly right now if you heard it for the first time, but just take it granted that, so the position, the center of this binary function, which we like to have this charge center, so we can calculate this polarization easily, is connected to the Berry connection in K-space. So it's kind of something you have to visualize in your head, and but this is very critical. So I mean, this is somewhere actually we can connect this Berry connection to the center of the binary function, which is very much like we talk about some geometrical object in K-space in the momentum, crystal moment space, but at the same time we can visualize it as the center of this binary function, the electron cloud, in certain sites, so that they are actually connected by this way. So either you calculate Berry connection, or you can calculate the binary centers and make a Fourier transformation, and that actually at the same way. The same is true for Berry curvature that we're going to do. So we'll explore a little more how we can understand some of the details. So before you go into some detail, let me just place you that once we know these types of Berry connection and so on, then how this is really connected to well-known physics that we know, we understand, like a quantum polyfan, which is just nothing but the dynamics of all electrons in an electric field. Everybody knows this, the two-dimensional electron gas under a strong external magnetic field. So this is the actually interaction of electron with external magnetic field, that we know that under the magnetic field we form a Landau level, which means that you have a circular motion of electron. That is actually exactly the same, the curvature by the magnetic field. In fact, the magnetic field provides a geometrical geometry within this electron motion under certain conditions. So having this integer quantum Hall effect is actually connected to having some curvature of the wave function we cannot distinguish. So, maybe this is all the proposal by Haldane. This is part of his contribution to its Nobel Prize, but it's the same the quantum Hall effect, but not by the real magnetic field, but by some of the topological connections in the lattice. So that is actually equivalence. But all of the things we can just describe in the same fashion that we say. That let's say that you have a Hamiltonian. Now you back transform in a K-space here. I just wrote Q instead of K. So this Q is acting as a parameter. So now taking derivative of this energy eigenvalue is equivalent to velocity. With this part I skipped in the earlier, that when it dealing with currents, the current means charge times this velocity. That is actually equivalent to like taking derivative of energy. But actually there's something more on this one. If you just take this as very simple, once you have a magnetic field or any Berry connection that acting on the K-space, this can be either that comes in as a vector potential inside. So at this time, we take this vector potential provided by some electric field, which is actually is an electric field times t. The time t is vector potential, which actually drives this k value, which we took as parameter, but now is in dynamical quantity. So once we have this term comes in, then all this the calculation we go through that, then we have actually this the velocity is not just the gradient of the energy, but it has a connection with this extra the vector potential, which is actually connected to the electric field, is actually connected to this Berry curvature. So it's like electric field times magnetic field in some sort of electrodynamics, which is contributed by this topology on this wave function space. So anyway, so once we have this way, then we can actually define. I'll come back to this point in a more heuristic way a little later on. But anyway, so in that way, we can actually have this quantum Hall effect understood in terms of Barry curvature. The same is true for this anomalous Hall effect, but this is just nothing but because of this Fermi surface, which is cutting through the part of the band. In the previous case, it's a completely filled band, so we don't have to worry about this occupation. But in case of metallic system, and part of the Broglie is actually partially empty or partially filled, so we have to count only the occupied zone of that with the same Barry curvature comes in. In fact, this is kind of a history of this all Barry connection stuff. As I remember, this is one of the first evidence that people discuss that is people. Well, this was the title of this paper. In fact, they said monopoles in momentum space of strontium ruthenate. Now, you remember the picture that I showed earlier at the beginning of my first lecture, that once you have direct cone, which is actually equivalent having a monopole inside the K space, right? Which is same as you put a single spin in the solenoid or magnet and rotates. And that creates the same Barry phase. That means a geometrical structure. So people didn't know before that this strontium ruthenate has some other band structure below the Fermi level, which was hidden, but nobody paid attention to that until you recognize this geometrical phase is playing crucial role. And so this is one of the first paper that pointed out by this is Dongfang, who is now the director of Institute of Physics in Beijing, and also Nagaosa and Tukura and their company, Terapura and so on. And so they look into this band structure of strontium ruthenate inside, which was hidden, and they find there is some structure like this inside this band structure with Fermi level is somewhere here, and they calculate that, and because of this, just this simple small crossing point, which was neglected by most of the people, and they acquired all this calculation tool and showed that it has a very strong non-trivial contribution to the whole effect. So that's kind of thing that we could have done earlier, long before the discovery of this topological physics. But now we can look at it in different directions. Another, I'm not going through in detail, but there is another interesting proposal after all those the fuss about monopoles in crystal momentum space. And people also figured, okay, why not then just look at crystal with this kind of Kagome style lattice that having the spins located at the corner of tetrahedron, they all connected to each other. But in this case, this strong local field, anisotropy field, acting on each side, actually that makes the spins actually kind of discrete spins connected in whole space. And in fact, they can actually map this types of geometry by having, if all spins pointing to the center of tetrahedron, they may say, okay, we have a monopole inside. And if it points all outside, so negative monopole. If it points outside, we can consider that as some positive monopole and so on. So they actually have made this one as a kind of theory that how you're going to understand all this. But eventually it came up in the same types of formulation, but in a more effective theory. So it actually evolved into a lot of this low energy physics by Nagaosa and co-workers on this so-called skirmish. That's the real geometry can visualize, but it eventually it's kind of a topology sitting behind. So those kind of thing is something that we can understand. So anyway, so this types of geometry effect is all over condensed matter system, and now we have to focus on so how we're going to define Barry phase, how we're going to define Barry curvature, and what do we know about topological invariance on the system. So then we have to say, okay, so I already showed you all the ingredients, but now we have to identify what's the real culprits of this the signature of topology of a system. So coming back to this very mathematical idea, the basic idea from the start, you know, this n-holonomy, the holonomy is something you just make a trace curve, but you try to measure some property following the curve. One of the examples is on cylinder. If you just move around the cylinder, you always come back to the same point. You can, but you can move around, you know, go up and down. But at the end, there is no trouble. You're coming to the same point, just like that. So when it is transported along some C, then you always come back here. But if you start from a little bit above this one, but you have no trouble coming back to the same point, something like that. So in that case, your position along this y direction, this is perpendicular to your motion or the path that you're taking. That's what we call this y, the vertical position as a kind of an holonomy. This is this little parameter that we take. But if you consider so-called Möbius strip, you all know about this little toy you play. In this case, you can also take some path coming back to the same position all the time. So you take something in your reference point, which is if I take some point in the middle and you go around, then you can come back to the same point. Now, the thing is, you start from a little bit below of that point and go around the same. Then you always end up with somewhere else by some distance. But if you start again, you go back, and you follow, then you come back to the same point. So you need to run not just once, you have to run twice to come back to the same point. So that's kind of measurements that we can make, and there is some number. Either you have a positive or negative, so you have to identify. So we'll. Maybe there is graphic that takes a little. Sorry. It's okay. I think this figure is a trouble. But anyway, so what is nothing. I just tried to show this picture as kind of a hallmark of what topology is to say. In fact, as you all know, you heard about topological insulator that has a time reversal symmetry. We call Z2 invariant. Z2 means it's a modular of 2. Means you have integer value of modular of 2 means 0 or 1. You have only 2 cases. So it's in some sense it's just it's too symplectic that you're not really counting anything seriously. So if I say some system or material is topologically non-trivial, means then you have to it's different from trivial ones. So in case of a Z2 system, Z2 number 0 is trivial, which is all we know. But then you have another class which is different from non-trivial one. So how are we going to identify? Well, there are lots of physics here going behind, which is just same as like a quantum Hall effect that I just described, which is actually acted by the presence of this curvature, which is acting as the magnetic field in the system. So. But anyway, so once we know this one, this the same holonomy that we know can be converted into all this connection curvature, and at the end you get this number, single number that represents this state of this topology of the system, what holonomy they have. So that can be either 0, 1, or 2, 3, 4, 5, any integer, or something else. Anyway, so it's kind of a discrete number that you're going to do. But anyway, the thing is, all we gonna find in condensed matter system, it's actually based on this picture, which I showed you earlier in my lecture yesterday. So if you have these types of crossing points, the cone structure, it can be a three-dimensional cone structure, or it can be in two dimensions, but just like in graphene. If you have a cone band structure in 2D, doesn't matter. So it is all going to happen just starting from that. And so it'll give you, this non-trivial connection and also non-trivial direct curvature that leads to quite different structures. So let me go through a few, not all of them, but maybe step by step. So the easiest one is to consider having direct cone without any symmetry constraint. That you have a direct cone, but not without any spin degrees of freedom. But whatever degrees of freedom in system you have, you can have this direct cone, which means you need two bases, just like what I showed in the beginning. So the fact that you have this one means you need this Pauli operator. That means you are having some dual bases or sublattice symmetry in different connections. Like in graphene, you have an A site and B site, which are equivalent. So you need to write your Hamiltonian in terms of those sublattice indices by that. That way, that you have already have some symmetry comes in here, but this one doesn't contain any time reversal symmetry in it. So this sigma is not for spin, the real spin that we talked about, but this is for pseudo spin that we talked about. So in fact, this is a degenerate in real spin space, so which doesn't have any structure at all. So let's say just neglecting or forgetting about this time reversal symmetry or spin, we just take this one. Then the first thing that we can get is, so no spin indices, orbital whatever, only just two sublattice bases that we need to get this spin structure or this cone structure. Then the only thing matter is we need to get this Chern number by some flux. But in K space, to have this non-trivial K, if there's no singularity in space, then you can choose whatever small pad over all this space that makes it trivial. Okay, just like this the flux that we calculate on the magnetic field. But if you have at some point you have singularity, that means you have this crossing point, which we can refer to this magnetic monopole. Then everywhere else is a trivial. I mean, if you take a path like this one, it's a zero. You see, it's going to be zero. If you take anywhere, whatever place you go, it's a zero. But if you circle around this singularity, the direct cone, then you get this integral should be 2 pi, and the Chern number should be 1. Okay, so having this one around this one, then I showed earlier in superconductor, what's going to happen is that superconductivity should destroy at this point. The same is on this topology too. So we cannot have our wave function well defined at this point, which means that the binary function is not going to be valid at that point, which is actually related to a previous question that our binary function, whether we can make our binary function localized. Yes, it is, if you don't have anything like this one. That means that if you have a crossing, means your band gap is closed at that point. So as far as you have such kind of singularity, then your binary function is not going to be localized. So that's what people call binary obstruction. So you can't really construct the binary function as we like. So no smooth function, function is defined around this point. But if you ignore that, if you go along the long way, but still you can't ignore this presence of Z, although this is far away from the singularity. If you go across this sum, then the C number is supposed to be 1. Okay? So regardless of spin, you are having topological invariance, which is what we call Chern number, that is actually connected to the presence of single direct points. But now it gets a little complicated when you have time reversal symmetry coming from system. And in this case, trying to explain what Z2 invariant means. So you have a time reversal symmetry means now obviously since we deal with electron, your electron spin needs to be flipped to the other side, right? At the same time, you have to make a complex conjugates of that. That's a time reversal operator that we define. And this is like a Kramer's degeneracy that we know very well, like in the system, that any eigenvalues on certain k point should be equal to on the other side. Time reversal points of that in the Brilonjo, they got to have the same energy eigenvalue. That's Kramer's degeneracy that we understand. So, but it's not just the Kramer, just the eigenvalues only. That means that our binary function for given eigenvalue, which is degenerate. So we might have the binary function, which should be double copy of the original one, right? So you have to distinguish our binary function into two. We have to split that up. But how are we going to do that? So there is a way. One of the ways to do is that since we know this binary, the state is symmetric. Sorry, the eigenstate is commute with this time reversal operator, the same as we constructed this binary function with translation operator. So we can construct the eigenstate of this time reversal operator too, right? So it's even with time reversal operation. You can have the same binary function, but for the time reversal operation, you can have the odd function minus, changing the parity to minus of the original one. There are two kinds of binary function exist. So there are actually the one binary function here with time reversal operation. You can end up to another one which has an even symmetry or odd symmetry. So we can actually distinguish that. So then you try to make a connection of moving this point all the way around over here. You should have make a continuous connection from one type of symmetry of the binary function to the another. So in that way, so that's the way we calculate this connection. The coverage shift depends on single shifts of this binary functions. So by this time reversal, what you call time reversal polarization means is that we like to divide two kinds, one connection for the symmetric case and the other case for the opposite case. So in such a way, then in fact, once you know all of this, the Chern number or connection on one side, then we can actually simply know all of the connection on the other side, which is just the opposite in direction. So one point k in this direction should go to the minus. So everything is just flipped. Your curvature also changes in the sign by that. So so this is just one example. Yeah, I suppose should have finished this one by yesterday, but it's okay. We can do it today. But anyway, so just to preview what I'm going to discuss next is that, okay, so that's there is just a Chern number, which doesn't depend on any other symmetry in the system. But now you have a time reversal symmetry, or in certain part of the Berlin, you have like a mirror symmetry on other operators comes in. Then we should be able to distinguish or combination of all that Chern number and different symmetry sector that will give us more ideas on the class of different topological materials. So I'll go through some of them one by one. So I was so ambitious that I'm going to cover all of it, but maybe my best shot is up to here, because there is some practical matter that maybe the students over here will go through in their hands-on experience. So, but I'll describe. This is some of the reiteration of what we discussed so far. but maybe some ideas with hybrid binary function and twist loop and so on would be the key. So far, any questions? So what some of the conceptual, the very general ones. So you're satisfied? Okay. So yeah. So let me move through. My time is up.
10:45.
Oh, well, I have plenty of time too. So, just to summarize what we have discussed so far, in a very simple matter. So now we're dealing with Hamiltonian parameterized by crystal momentum K. Okay, we understand that. Okay. So then we define K like this. Of course, we can put additional the vector potential, like an electric field comes in, then you have a vector potential A with like electric field times T that comes in right here. Okay, so that way we can actually treat some of them. If you put extra magnetic field, other than the curvature or connection within this Hilbert space, that should also go over here too. But they are actually connected to this real or interact with the real magnetic fields too. Now, so to understand what's going on here, we'll use Barnier function, but it's so-called maximally localized. That I briefly described why we choose maximally localized. But, so this is the space that we're going to do. Now, here we try to introduce a little bit an additional concept of using hybrid Barnier function. The hybrid means it's you in the real space you have a x, y, z direction. Okay, so now you say, okay, I'd like to take this ky and kz still in k parameter space, but I would like to just take the binary function along x direction. Means I take this growth function, but leave out ky, kz as momentum parameter as it is, but now we only take the parameter case summing up over kx, which means that we visualize the quantum state Hilbert space vector in ky and kg space, but along x we only deal with some real space coefficient. But the reason for that is that counting this binary part that we described, let's say if take this r as only position operator for x along x direction, then that is actually calculating this binary center. Center of the binary function is directly connected to the Berry connection. Okay, so we like to explore the Berry connection along x that is connected to the binary center, but we like to move it around in the k space in the parameter momentum, crystal momentum space. In that way, we'll see that how this Berry curvature is actually present on the system, and depending on how we move around in ky and kz, we can identify the Chern number that we would actually like to get. In fact, it's hard to calculate. The Chern number is only defined on the surface, right? It's not a three-dimensional object. We have to define some boundary, and you define a surface somewhere. So Chern number is defined on the surface. So if you take a three-dimensional crystal, then the volume is not important. So if you have a crystal, then you cut some surface. Okay. Now your Chern number is defined within that surface, but you can cut this way or that way or that way. So you make like a sixth surface of that, and you count what Chern number on each face it has. Okay. And you can add up, and by visualizing that, you can see whatever direction you cut, you always got non-trivial Chern number. Okay, then this is a strong topological integrator. Okay, it's a strong topology. But some system, depending on the direction you cut, it may have non-trivial Chern number on this direction, but if you cut this way, it's a trivial. Okay, or if you cut that way, they can be trivial too. So if you cut very well on certain direction, which actually preserves some mirror symmetry of the system, that it might come up with some another Chern number which we didn't expect. Okay, so that's so-called mirror Chern number that we call, which is hidden. In fact, if you just take the normal Chern number, it's just a 0. But if you take the mirror symmetry and separate out this Barnier function or some state in that, then it may have some net effect, a non-zero, non-trivial power. So that kind of thing can be possible. We can so take this one as kind of the tool that we visualize this Berry connection or AM. So in that way, so this Barnier center can be used with combining this one with this center. So we have this Barnier charge centers. So X is a center of Barnier function along X direction, but it carries on the parameter in K, Y, and G. And you see this integration is something that you look for. So if you integrate either, since we already had the integration of Kx, so if you integrate the same thing along Y or Z, then that's directly connected to our topological charts. This Berry curvature of the system. So by that, so if you integrate along the Y direction from 0 to 2 pi, so you are parentheses. So if you integrate this 2, that is directly connected to Chern number along X and Y this surface. You see, the previous. See, so this one already integrated along Kx. So if I integrate this along Ky somehow, then you are actually integrating all over a single surface, closed surface. So that's the Chern number that we like in Kx and Ky surface. It's defined with the Kx and Ky to the surface. So in that way, then the difference of between these two is actually, we already know, this charge center is interpreted by the polarization that I just described earlier. See? So this integration of Berry connection is just connected to polarization, charge polarization that we know. So but the charge polarization can be different for Ky0 and Ky2 pi. But just going through this one Brillouin, with one translation, they supposed to end up they can end up to the same point, and this is 0, means it's trivial. If they end up with net translation of EA, the polarization of the unit cell, then it ends up to the non-trivial topology. So that's how we're going to use this hybrid Barnier center that is actually directly translated by the polarization in the system. So if you say this way, then they call it as a hybrid electronic polarization of that. So that's actually a function of Ky. So just monitoring this, how this polarization changes along Ky, or translating along K or Kz, then you can see that like if you take this one as Ky, then you start from 0, and once you translate it 1 to pi, then you end up to the different point. But still, this is also a translation invariant by G, or 2 pi over A. So this is actually equivalent to that. Okay. So this is sort of connected to topology. So this is, if you visualize this is more of like a torus. But if you have something really confined like that, then you end up just by having very simple trivial problems. So, in fact, I'm going to take a few figures from this paper. That's by the Vanderbilt's group, and actually many groups work together. They work together to make this so-called put in a Z2 path, but it has many different cases. But unfortunately, it's a numerical implementation of this hybrid Barnier center, but it's just a single tool, but it's not really, you can't solve everything as you wish to. But you have to look at the problem. You need to carefully choose the numerical tool that you're going to apply for that. But so it's not a full solution you can get. but at least you get some tool that you can explore which you like to study. So just taking just a very brief idea of what this would look like. So this is also taking a nice, beautiful figure from this paper. So as I said, it says ky is a parameter, and now you measure the binary center along x direction. Sorry, I should put x here. So this is a binary center along x. So for given ky, so that's a periodic space. But if you just look at the one-dimensional projection of that binary function, then when ky was 0, then the binary center would stay here. Okay. But now in different ky, moving into the different Lagrangian, the binary center will move. It can move like this way, all the way, but this is periodic. So this is actually connected to that. So you have a loop here. So in that case, moving along this Lagrangian, it doesn't really move around too much. So it just stay there. So this is kind of trivial thing. Maybe you take the average of this. That's the physical polarization we expect from the system. It's a ferroelectric. Okay. But now the thing is that if you get something strange or non-trivial topology, then this charge center will move over here. But this is a periodic, so this one is periodic to that by translation of A. The same as translation of 2 pi in momentum. It's all periodic. So this is kind of torus structure. So this will come back here, and then we move around, and after 2 pi, they come to the same. But now they have moved around like one circle. So if you make this torus structure, then this type is corresponding to that. So it is like one winding number 1. You just go around. So you have a cylinder. This is wind one time. That's what we call tran number 1. But also you can actually wind twice, which is corresponds to number 2, where this is like a bull coupling. That's how we distinguish topology of a system, which can be described by having this. Okay, so with this hybrid formula that we have. Slow. Well, I can take question while this will respond. So any questions? It's clear so far. Okay, so maybe to get more feeling on what's this been realized in real system is that suppose you have a system in real space like this. This is periodic system of like take some closed material, and you apply an electric field along x direction. So electron will flow like this. In this case, I just chose the x and y in a hybrid term in the previous case. So it's a little bit very confusing. So in the previous figure, this is y and this is x. But you understand what I'm saying. So so you applying the electric field along this direction, then let's say what's going to happen? We have an electric field along x direction, means the electric field has components of x only along the x direction. Okay? Now your k, time evolution of k, is driven by the electric field in momentum space. So if we just integrate, this is first order differentiation. It's easy. So your kx is proportional to time t in linear fashion. So you're moving your kx along x direction like that by time proportional to the strength of the electric field. Now, for the time to change along the kx, that it'll evolve from 0 to 2 pi over 8, okay, by the electric field. But how long would it take? I mean, previously, I said this is parameter that I just move by hands, but this is a physical system that by applying electric field, you can change crystal momentum k from 0 to 2 pi over a by the time of delta t0. This delta t0 can be calculated, by putting delta t0 here then this difference is supposed to be 2 pi over a. So the time is calculated like this. Now, suppose that this is a kind of a quantum Hall state with non-trivial Chern number. That means moving along this k direction, you calculate the Barnier center, the hybrid Barnier center along y direction. So suppose that the Barnier center is sitting here. So this is the real space, but if you move on to the momentum space, the Barnier center is on the edge of the corner of your periodic unit cell. But now, moving along this direction, the Barnier center can move along like that. Of course, it could move like this way. That's trivial. Or it could go up like that and come back. Also trivial. Nothing happens by moving one cycle of that. Of course, if you move like this one, then it's literally zero polarization. But it could go like this, like moving a circle, like a Landau level, the Landau orbit. You can make a circular orbit like that. It could have little polarization, but not much. It's not topological. But if you have something going from here up to there in the periodic unit cell in real space, and the Barnier center change, that means your polarization is moving from 0 to E times charge times unit cell size A. So its polarization goes up like that. But since it's periodic, that moves will come back to this point. That means they're here, that they move around again and again and again. As time goes on, then the charge polarization is actually going up and up and up. But by each time, you are literally pumping a charge from this side to that side by one unit cell. So every unit cell is actually, processing along this direction. So your unit cell is moving one step, one step, one step, and so on. The charge is moving forward. So you are, by that, actually, you are creating a current along this direction because your delta Q, since each step of your crystal momentum varying from 0 to 2 pi of A, you are actually moving charge E along this direction. But I take a C as 1 in this case, but this one could go winding twice. That means it could go up like this and up like that and so on. Then your Chern number 2, then each cycle you are pumping 2 electrons across the unit cell. So in that way, your current is defined by Y of delta Q over delta T0. That's the definition of current. And then by putting all this number, you get the current along Y direction, which is normalized by field currents, in this case, is proportional to the electric field along X direction. Now, current is flowing this direction by the amount of that, which is what we call as anomalous conductivity. That you have the field going along X direction, your current is flowing Y direction. So this is the anomalous conductivity that we know. This is anomalous quantum Hall that depends proportional to charge, the Chern number C on this direction. So this way you can visualize clearly that what we are going to discuss in the Barnier center and the hybrid Barnier center along Y, but you're moving your parameter along Kx direction. So it's all connected, and in fact, this is known in the earlier stage of all this topological physics. People describe this as charge pumping. Murakami and Nagao-san and all this Japanese group have studied looking into this anomalous Hall behavior. And at that time, they didn't have, actually, they had a feeling or picture inside, but they didn't put it in a topological matter, but they described it as a charge pumping. Very interesting phenomena because by applying the electric field along X direction, you're going to pump charge from one side to the other constantly. But actually they have made designed specific settings of experimental system that in fact really pumping charge from one to the other by running cycle on the other direction. So very interesting configuration. But I think this is a very simple way to visualize how this Chern number is actually making up real phenomena that we see in a system. So that's how we're going to understand all of that. So this is very clear, but trouble is the real band structure that we have is not so simple. You don't have only single band. So in the beginning, you want to say, okay, I can just draw this hybrid binary center. Then you're gonna have one line going like this. Okay, so we have chart number 1 or 0 or 2, but in reality, it's not as simple as that because you're gonna have a bunch of bands in a system, but you never know which one of them will contribute to this chart number. And to make it worse, in some cases, actually, one of the bands has +1 contribution, and the other one has a -1 contribution. You see all of the example here. It goes to +1, but the other one goes the other way around. So everything is all mixed up. So it's very difficult to sort out how this the thing goes on. So people have made, okay, we have a better way to sort out all this. So instead of dealing with one band, so that we can make this projection operator. We define this manifold, n band manifold before, and we have this the basis function for the k space with different band, but everything goes in occupied state. But if you make an operator like this, I mean, the x is a parameter, but the y is our local Binary center. Then the position operator projected on this part, the P, this is unitary matrix, sort of a unitary matrix, and that can actually sort out. But there is also a caveat that we can actually multiply by arbitrary m by m unitary matrix before and after. Managed to actually describe something yesterday. So when you calculate this Green's function or something, we also can do all this unitary mixture of unitary transformation, but it's there is no guaranteed or way of choosing the best one. There is nothing like that. So that's where the life gets complicated, and you have to be knowledgeable and or smart to choose the best one. But anyway, the thing is, suppose you can manage that, but it needs a lot of patience and devotion too. But anyway, so you make up these types of operator. So you put back everything like this, and they put the name of Wilson loop. And originally this was used on like the quantum field theory that to manipulate all that. But we just use the name, but it's nothing but just you're gonna sort out your bands in M manifold, which actually you can sort out in different chunk number bands in different ways. So this is just a simple example of that. Like you have 3 bands, let's say C1, C2, C3. It's a very simple example. C1, you have a like 3-band system. The one of the band, like the first band you have the bottom one is trivial. One of the bands, you have 3 bands, but one of the bands at the bottom is trivial. And second one is non-trivial, but has a chunk number -1. That means it's winding not clockwise, but it's anti-clockwise. Okay, but the third one has a chunk number 2, means you are winding twice in the clockwise. But overall, then if you put them all together, then what you get is by summing up all of this, by the taking out the position, then you get chunk number 1 because you're going to add up all of the 3. Okay, but the thing is, this is a bit complicated because maybe you can make a unitary transformation of these 2 bands. One has -1, the other one is +2. Then you can make some combination of unitary transformation of these 2 to sort out that unwind this -1 to 0. Then you have a net 1 going to only 1. So in such case, these 2 will, after some transformation, you can identify these are not just trivial bands, but everything just focused on the top band, which carries chunk number 1, which is the same as the total chunk number of these all 3 bands that we have. But in practice, it's actually I've made by the time that I've made come to some of the example of that. But And having all that, I mean, this is sort of very the abstract expression of this number, but that's sort of thing that we have. You may face in real calculation, but if thing is very simple, then you can sort it out without any trouble. But sometimes if you make some kind of topological transition from chun number 1 state to chun number 2, then you need to identify where the extra chun number 1 comes. And in such case, it's a little bit tricky to see what's going on. So now we apply the same idea for the topological invariance that we just described. So I don't need to go through this one, but in this case, in real case, I mean, originally, when first the topological invariance is proposed, came Mel and the original idea was very, very complicated mathematics that people had put in on this the identifying topological phase, so-called calculate Hopfian of some complex n-byte weight slated determinant and so on. It was too complicated. So the first time when I tried to identify some topological one, and actually they made very nice summary of all this complicated theory that you can just need to look at the symmetry of wave function at so-called time reversal invariant point, where it doesn't get any mixture of anything. So you just need to look at the symmetry, real space symmetry of the wave function, even or odd, and that actually represents this chun number, the topological character of those wave functions. But anyway, but later on, that can be verified by integrating all this real integration of this very connection and also very curvature. But today I'm not going to describe all that complicated thing. But anyway, so this time go through the same thing based on this hybrid divided function. So the key point is that you have a time reversal symmetry, so you only need to look at only half of the Bernoulli, because the rest of them is actually just copy of that. It's the same. This is equivalent. They are connected by time reversal operator. So if you know something here, then of course you know what's going on the other side. So that's what the basic thing. But now in practice, I think it's easier to put it this way, which is easy to understand. We know the Kane-Mel model, which I just mentioned. This is the prime example of so-called quantum spin Hall effect. What is quantum spin Hall effect? We said quantum Hall effect is what you just described. The chun number 1 state, that's a single Landau level. If you have a quantum Hall effect with chun number 2, means you have two Landau levels of the same spin. 10 minutes. Then you have a non-trivial chun number, so we don't count any time reversal symmetry whatsoever. But if you have a time reversal symmetry, then as I mentioned, we have one spin-up electrons having chun number 1 like that. But if you have the spin down, which is the time reversal partner of that, will go through the same, reside in the same Hilbert space with chun number -1. So if you add up with the +1 and -1, with this picture, anyway, then you end up. I mean, you have 2 copies of this sigma. So I should write in summing over to the fibers. Then you have the spin up is 1. Then the integration of spin down is going to be -1. So your total chun number should be 0. In fact, Kane-Mel came up with the idea that this original Haldane model that describes mimicking quantum Hall effects with magnetic field with a curvature in the K-space. Now he introduces, or Kane-Mel actually introduced the same lattice system with spins, spin up and spin down, for the same curvature in the K-space. And in that case, that will have, for spin up, you're going to have 1. And for the other side, you're going to have another, the opposite. So if you just add up C plus and C minus, if you just add up 1 and -1, then obviously it's going to be 0. So it's not a chun insulator at all. So But if you have a, but it's not trivial field because each copies of spin will have a Chern number. So he devised a new quantum number that actually try to sort out what's behind. So it tried to take C plus for spin up electron Chern number minus spin down Chern number electron. That means 1 minus 1 means it's 2. Is again this becomes 1. So the thing is that this is equivalent to having this one time reversal polarization that taking like the spin up copies and spin down copies. That is actually directly related to this Kang-Wang model with 2 copies of spin, the Haldane model. That means you have a same Landau level running one for spin up, 1 for spin down, or with the opposite the Chern number. But now in total it's 0. But now if you can sort out a Z like this, then okay, that's what it is. So this is same like dealing with like the magnetization of a system where we deal with spin up electron minus number of spin down electrons. This is exactly the same copy. But now the interesting thing is we can view this one in this way, and in terms of this hybrid, the hybrid binary sensors, that you have a copy for +1, which means a spin up, let's say. Then the charge center for the hybrid charge center, I should say, is the binary center for spin up goes like this one, like that. So it ends up by winding clockwise, number 1. But in the other copy of the Haldane model that has just the opposite curvature goes not this way, goes down like this. Okay, so that ends up with -1. So if you add it up, total is 0. But when you draw this binary center in the picture, you're going to end up going like this one. You have some crossing going like that. So this is the way. So now we have only 2 bands, which is actually hidden, but for the same looks the same band. But if you draw the trajectory of this binary center for one copy and second copy, then you should see this exactly symmetric ones crossing spanning the K expression. So this is but there are many different cases. So this is very simple case like this one. You have one going like that, or another going like this. Of course, this is the typical topological insulator with Z2 number 1. But they actually evolve in different way. But this is trivial. Nothing happens up here. And also, there is something like this one actually is winding twice. So +2 in one, the Chern number 2 in one direction, minus Chern number 2, -2 in Chern number in the other direction. So this one ends up like that. This total is 0. This is non-trivial. But non-trivial, but it's actually a trivial because if you wind twice, in fact, it's the same as you can unfold it to the original one. That's what we learned from SU2 group symmetry. But anyway, they have made this. You see this green bar. So there is a rule like this one. So if you draw some line somewhere in your this hybrid center plot, then if it cross once, then it's non-trivial. If it cross if an odd number is non-trivial. If it tries cross even number, then it's sorry. If it cross odd number, then it's non-trivial. If it cross even number, then it's trivial. But you have to digest all that logic behind. But they actually make up some of the stories like that, and it's pretty. You need some time to get on. And I also have mentioned that something like mirror symmetric topological phase. This is sort of a higher, going to the higher order. You can also look at the edge of this crystal to see how it works. But in terms of this symmetry, that everything. If you draw like n bands and you draw this the hybrid Barnier center along Kx and along the Ky along K. Sorry, it's mixed up. This is Ky supposed to be, then you have a the hybrid Barnier center along X direction. You see there are a lot of crossings going like here. See that? But it's hard with. If you do the calculation, it looks like this one. So it looks as trivial, it's symmetric, it's nothing, it's hard to visualize. But the way to do it is that, as I mentioned, within this plane, every wave function is supposed to carry this mirror operation symmetry, either even or odd, because it's a binary operation. So eigenvalue is supposed to be 1 or -1, right? So you track all of this Barnier function and see whether it carries extra quantum number for the mirror operation for even or odd. So you just trace them and going through, then one of the lines should go like that, the other line goes like this. So this is a mirror quantum number. Sorry, in this case not one, it's I or -I. So it's two different quantum number. So you sort out among these many states of this M manifold, you can take, since the mirror operation was split in two, so the half of M manifold with this mirror operation quantum number I will be like this. Another one with mirror quantum number -I will look like that. If you superpose these two, then you go like that. Okay. But for this one, if you trace up how this will go up, then there is a clearly line going like this. Okay? So that it actually goes like it's winding twice like this, and the other side is going winding twice like that one. So at the end, you end up to 0, but you just take out this two different mirror term number, the difference, just like a Z2 topological insulator, then you can identify there is an additional symmetry or topology exists in your system. So there are so many things to go through. So it depends on how you do, and also the same thing so your the charge center behavior is actually connected to the edge state behavior in some way, but I think it is just a little more complicated than that. So anyway, so there is a way that you can go through. That how the system has, if system has certain symmetry, then you n by m this unitary transformation, you can actually sort out this m by m unitary transformation with respect to certain additional symmetry operator, like time reversal, mirror, or skew symmetry, and so on. So that's the way that you can actually analyze. So in the last couple of minutes, let me just flash you that so before this the Barnier center type analysis that we carried out or discussed, but still we use the same technique as it is now. This is just after this is in 2005. So when people get some idea on this this calculation of the Berry phase in the system, the Fukui and Hatsukai and Suzuki, and they published this. Their calculation is this Berry phase and discretized Prolongation. So it's not worth just describing it simply, but you can actually write down everything in discretized form of this Berry connection and also Berry curvature flux, Berry flux, what to say. So based on our the Hilbert space vectors on described on each K point. So the thing is, surprisingly, that this taking this Berry connection in discrete form is, in fact, it is it's less complicated. And also, as far as we take this grid, the grid may not need to be very fine, but sometimes you never know where this crossing point is. The direct cone, the crossing can be in either a symmetric point, the symmetric edge of the prolongation or the gamma, but quite often it happens in the middle of the prolongation in general points. Well, you never know where there exists. So, but if you take this discrete grid, not fine enough, so you miss this. Your grid may miss just the presence of this direct quant. It happens in fact. In such case, you're going to just miss it. But anyway, so that's kind of caveat about this. Anyway, so far it has worked pretty well, and we used all this way and implemented in OpenMF. And earlier days, even now, if we just need to verify our analysis with the Barnier Center, we calculate this veriflux explicitly on discrete basis, but in different sections of the Bergmann, and it works. And then there is the recent version of that. I think there may be others too, but this is just the extension of this Fukui's algorithm. Was actually they used the same discrete grid to calculate this veriflux, but now they actually have extended it to just like so-called tetrahedron integration of our Bernoulli integral. You know what tetrahedron integration is? It's implemented all of different electronic structure code. It's not just a simple mesh average or something, but you have to divide your Bernoulli to cut through. For example, if your Fermi surface is lying like this, then you cannot take any simple average of this corner point. So you have to know exactly where this Fermi surface is cutting through. So and that part you need to apply for this old trick of using tetrahedron integration. But also you can make a 2D version of that and putting it all together to do this slice of that based on your numbers calculated at the corner. So this one actually makes up more of those this in detail, and so I think I don't need to go through. So in OpenMF homepage, if you go through, then this is how the Fukui's the formula is implemented in the code explicitly. And some of the one, this is Taishiki Ozaki had written up some the realistic way of putting these elements out of it. But I think that it is a little bit special for this local type binding like formulation we put on OpenMX. But same thing applies for Barnier 90 and all the others. So I think you can just put that. But I don't think I have time for going through some examples. But yeah, but I will just take the questions. Probably finish. Yeah.
Hi, thanks.
Yeah.
Yeah. Hi, nice talk. I want to ask, what Hall effect?
The properties that you showed is quite similar to quantum Hall effect. Is there something that I missed, or what is the difference between quantum Hall effect and anomalous Hall effect?
Basically, there is no difference. Yes, you're going to measure if you have some crystal. In fact, it's not being realized in experiments yet. We actually made many proposals that some system with particular geometry and composition, then it will have a non-trivial topology, the Berry flux. So that system will become quantum Hall system without any external magnetic field. So experimentally, you don't need to apply magnetic field, but you get a quantum Hall effect in that.
Okay. And one more question. So maybe I missed it. So magnetic field breaks time reversal symmetry, right?
Right.
So when you're talking about time reversal symmetry and applying it to these kind of states, what meaning does it have? Or is it for some other systems?
Oh yeah, actually, but yeah, it's a very nice question. So you are asking that, when I say this, some system with this non-trivial topology will show up quantum Hall effect, right? Sort of quantum Hall effect, but without magnetic field. But the caveat is that, but the system that we're dealing with has non-trivial this topology. But if it still maintains the time reversal symmetry, okay, then you're going to have an exact copy, another copy with negative Chern number in the system. That's guaranteed. So you'll never see such effect. It may come up with topological insulator, so you may see something going on an edge, which is broken spatial inversion is broken, so you're going to end up having some edge state coming up. That's what we all know about. First about this topological insulator. Everybody is searching for this effect of edge state, but it's not clearly demonstrated so far even yet. But theoretically, it happens only edge state. But so to have this quantum Hall effect really realized in real bulk, then you need some system already, a system with a broken time reversal symmetry implemented. That means that you need some magnetization order that should be there, which breaks time reversal symmetry, and you have a non-trivial topology with Chern number that we described. Then you end up. So it's not without any magnetic field, but the condition is with broken time reversal symmetry and non-trivial topology Chern number, then you're going to have quantum Hall effect. I should restate that.
Okay. Thank you.
It's very nice point. So to have this quantum Hall effect to realize, we need some system with broken time reversal symmetry. It means that some ferromagnetic ordering should be there with non-trivial topology. Yes. Thank you.
There is some system, like the paramagnetic system, but they have anomalous Hall effect.
Yeah.
What is the reason for that?
Yes, anomalous Hall effect can have many origins, but this one we call is a quantum anomalous Hall effect. Means your quantum Hall conductance is integer value. Okay, but most of the anomalous Hall effect we can have. In fact, even with small magnetic order, magnetic spin system, will scatter electron. That actually brings up with some extra effect like what we saw, but it's not the quantum level. I mean, e square over h in the units of e square over h. It's not all the one. It's just like 10 to the minus 3 or 10 to the minus 5. Very small, normally. So that's anomalous Hall effect that we described. So that's usually derived from the magnetic scattering, either skew symmetry or some orbital effect and so on. There are so many theories about those, which is not but this quantum units. This is very unique. It's very strong. Yeah, so there's a question here.
So for anomalous quantum Hall effect, is it necessary to know the details of the system or the material we're working with, or like quantum Hall effect, which is completely material independent?
It depends. But all we need is a non-trivial topology in K-space. That's all we need. But what brings up such kind of non-trivial topology? It depends on the materials we have, because it's a properties of our Blow space, the K structure, the K-space geometry that we have. So it requires some particular set of spin-orbit interaction and also orbital hybridization and so on. So there are. So it's not just a unique or independent, not a very general one, but you need to find the right system which gets this non-trivial topology. And some of the examples, some of the works we've done was we've been searching for 2D meta-organic framework system that carries a particular geometry within the two-dimensional system, and that has magnetic ordering in the very high temperature, but has a non-trivial Chern number in the system. And so there are several proposals of that. But I'm not so sure what the nature is actually saying. But we need to find the real material actually we have proposed based on our theory and calculation, but experimentally they cannot really make that system as pure as that. Okay. So we also know that we have predicted, for example, everybody knows like chrome silicon germanium system. Chrome silicon telluride system, for example. Yep. And that we know is a 2D materials that we all know. But But as it is, it's just a trivial insulator. But if you dope the system by 1 electron per unit cell, that's a very challenging thing to do. But theoretically, we can do that. We can put our Fermi level a little higher, and we actually made a definite prediction for that. And if you just charge the system by 1 electron, then your Fermi level just lies in a small spin-orbit gap in the system. And that system is also magnetic because of the crossing the electron moment. But the gap lies in the tellurium p band, a little bit of hybridization. That is actually must show quantum Hall effect. But we made a proposal like that. But the thing is, many, especially some referee say it's almost impossible to dope it by 1 electron per unit cell. But we don't want any chemical doping, but we need really, literally, without breaking any symmetry, just putting 1 electron in the system. So I hope that these days people can dope in such a high amount. So I think it's somehow, sooner or later, people will see that. Yeah.
Thank you very much.
Yeah, nice talk. Can you please comment on the efficiency of the Fukui's algorithm versus if we want to calculate it through one-year function? Because I ask this because sometimes calculating through one-year function is kind of easy, but getting the one-year functions might be very difficult for some.
Very, very good point. So yeah, sometimes it's quite difficult, especially maybe I can just flash a little bit of that. Yeah, I was going to give you some real practical. Maybe this is one of the examples. I mentioned that I mentioned this chrome silicon tellurium case. The thing is, this is a real band structure we calculate. But if you see this one, this is ferromagnetic, and there are 1, 2, 3, 4 bands. That's a manifold that we discussed. It's a real world example. And if you look at this one, the real calculation from either VASP or OpenMX, you get some overlap of some unwanted manifolds of band interfere with the bands that we want. What I discussed, 1 by 1 electron doping, the Fermi level will sit right here, in a doping level. So we need to take care of the topology on character of this manifold. But if you want to do binarization, you can't really do much about this thing, the crossing. But there is a technique you can do, but as I said, it requires more manipulation inside, which is not easy. So one of the ways to do is, okay, you manipulate your calculations artificially, so you lift up all this band up somehow, yeah, some way, and that's one way to do. And but if you can't do that, then the best thing you rely on is just going through the real using Fukui's formula that you just calculate explicitly what each one of them. In fact, I mentioned that you see a lot of crossings along the symmetry line here, like that, right? But even in the very general points of the Broglie, you have many of those crossings too. So in Fukui's calculation algorithm, you have to apply the grid pretty carefully. So you have to check with different mesh grid and how they really come up with the same number. But at some point, because we also did a lot of things with this, like applying external magnetic field, then actually external magnetic field also controls this the band crossing change too. In such case, it's very difficult and technically, so you have to go through all of that detail. Yeah. So, but anyway, so it is better, while you're running this binarization and do all this. It's good to have cross-checking, but in one way, since you already have the code and you can run and calculate it, it doesn't take really long, but it runs that way. So you better check in both ways to see. Because sometimes even with binarization, if you have some symmetry mixture of that, then you have to identify right additional code to get this eigenvalues of a symmetry operator, or you have to index your wave function based on those particular symmetry operators. So that requires another effort to do that. So still, yeah, so a lot of things go.
Thank you. I have another question.
Oh, yeah.
So, for a Chan insulator case, 2, -2, and 0 all are different. They have physical consequences in the system. But for a time reversal symmetric system, why 2, -2, and 0, 0? I mean, the copy of 2, -2, and 0, 0, they are considered as in the same topological class.
The thing is, you have yeah, this is actually ferromagnetic, so it's our questions. You're talking about system with time reversal. It's just like a band crossing. You know, if you have an even number of crossing, then you can actually reorder two bands with a gap, because they belong to the same sector. So you cross twice means that they can be in two separate bands with two different bands. But basically, that's it's an easier way to visualize. But if you have only single crossing, then there is no way you can unfold it. Yeah. If you fold it twice, you know, and SU2, you can actually, it's S2 folding, rotating 4 pi is actually same as 0, right? Yeah. So you can have that concept in it. So that's the easiest way to do it.
Thank you.
I know there are I know there are lots of questions, but I guess we have to come back at what time? before we.
Oh, yes.
15 minutes. We have
It's
just
15 minutes. So what I would suggest is the following. In the
You
interest
can
of
come to me.
yeah, you can come and ask the questions for you directly, and we can just break the session if that's okay with everybody. Yeah. Okay.
All right. Yeah. Thank you very
Thank you
much.
very much.
Yeah. Oh, sorry. So there was.
Oh, there's a question over here as well. Sorry.
That question can be answered.
Right.
Yeah, please wait for the.
I think I answered that.
So you want to answer? You just have to answer.
Yeah.
You can also ask now the 1 year.
No, that we cannot do. That's something else. That's anybody. Right. Yeah.
Let the students ask first.
So we have only 10 minutes. So please go ahead.
Yeah. Yes. Let me just,
Hey, my bag to Thana, वो कितने लेके मेरे को और टी-शर्ट that's 42 100